So let's look at the first type of model, which is AdaBoost. So AdaBoost, we build decision tree. We just have one split. Okay, and such a decision tree are called as decision stump. What they are called? They are called decision stump, and they are built sequentially like any boosting scheme. The training observation where misclassification happens, so their weight is increased in the next layer. So in nth layer, if I make a mistake in n plus 1th layer, that observation where I made a mistake, I will give more weightage. So I will not allow the student to make a mistake on the same thing where he has already made one. The final prediction, the votes are weighted based on the classification performance of that decision stump. Okay, so what we intend to tell by this is that you take the classification accuracy that at individual level, individual trees are bringing in, and then you are weighing it. Okay, based on the classification accuracy they are producing. So this is how a decision stump will look like. Now we are again going into the algorithm part. So what we are going to do is, initially we are giving equal weight to all the observation, which is 1 by n. Why 1 by n? So if you have like 25 observation, all observation will give equal weight, which is 1 by 25. And then for m equal to 1 to m, fit a classifier GMX to training data using WI. Okay, so WI needs to be used, and then you compute the error. So see here where error is coming in. What is this I actually? I actually tells that where the actual value is not matching the prediction. So this is the error. Generally, what we do is we simply calculate how many errors are happening. Okay, how many cases the actual is not matching the prediction. But here what we are doing is we are also using the weight. Okay, so you are getting a weighted error. And now what we are doing is you are computing something called as alpha m. This is the weight of the decision tree, and this is a function of the errors. So naturally, if you make less error, so 1 minus error is the numerator and error is the denominator. So naturally, if you make less error, then your weight will go up because the numerator will go up, right? And what you are doing is, for the next iteration, you are changing the weight. How you are changing? You are changing based on this. So if if there is so this is doing in an exponential level. So if there is no change, then it is going to be e to the power 0. E to the power 0 means 1. So there is no change in weight if you have made already correct classification. However, if you have not made correct classification, then the weight is increased. And finally, your output is like this. So this is how you can understand the formal notation of an algorithm. Okay, now let's look at 3 classifiers and their classification accuracy. Okay, so if you use that classification accuracy versus voting, that if their accuracy is 0.8, then error is 0.2. Okay, then it is something like this, that as you see, it is a random guess. The voting of that particular classifier is very less, and as it goes to very close to 1, its weight increases a lot. Okay, but there you can see that there is a kind of exponential trend over here. So that's how the voting power increases based on the accuracy. Now let's understand weighing of the samples. So let's say these are 5 observations, and for 4 of them my decision was correct, and for 1 of them it was incorrect. So as there are 5 observations, the weight of all of them were like 1 by 5. So this is the first stage. Now what I'm going to do, so see at a very high level, okay, see how many cases it is right and how many cases it is wrong. So it is right in 4 cases and wrong in 1 case. So I can think of, so if I was thinking of that 1 minus alpha by alpha, so I'll get a multiplier of 4. Okay, because I am getting incorrect. So it is like 5 minus 4 by 1. Okay, so I will get a multiplier of 4. So what I'll do, I will multiply So 0.2 will not change because I have made correct decision, but this will get changed to 0.8. The first 4 will not get changed, but the last one will get changed to 0.8. Okay, so far so good. Now I need to scale this back again to 1, and it will be like 0.825, 0.825, 0.825, 0.5, sum to 1. So now when you build a classifier, you know the error, if that makes an error on this particular observation, it will be highly penalized. So that's the objective. Okay, and when it comes to prediction, maybe you have 4 stumps and the first stump says class 1, the stumps 2 and stump 3 says class 2, and stump 4 says class 3. I'm just going to look at their weight. Okay, so the first class has weight of 3, the second class stump 2 has weight of 1, stump 3 has weight of 1, and stump 4 has weight of 1.5. So I will sum them up, see where I have more weighted votes, and I will go by the decision. Okay, so that's the overall scheme of AdaBoost. Okay, now some of the comments about AdaBoost is that it is considered as a super algorithm, and people thought it to be a silver bullet. Okay, but there was some skepticism, and some people were thinking, no, it is just overfitting. Okay, the overfitting problem actually existed, and particularly it was prominent when the data has a lot of outliers. Okay, and AdaBoost was, and in that case, it was very unstable. Okay, so professors from Stanford Statistics Department actually came up with gradient boosting, or GBM. Okay, so this is one of the very important algorithm. Okay, and it is quite complex also, but I will still try to give you a fair amount of understanding. So what I'm going to do is I am going to discuss gradient boosting for regression, because understanding for regression is easier. Okay. So what is happening here over here is that, let's say I am trying to again do a box office prediction. So I have this number of stars and this budget available. Okay, so this is the same example. What I'm doing is my first decision tree actually, so it follows a different approach than AdaBoost. Okay, so it doesn't have that weighted option and all that. Okay, so what it does, the first decision tree simply predicts the average of the actual values. So if you have 4 observations, the average is 70 over here. The average is 70 over here, and look at so the first decision tree actually predicts it to be 70. Okay, now the second decision tree comes to play, and the first decision tree was taking these as input variable and these 2 as input variable and these as the output variable. The second decision tree actually finds the residual. So this was the prediction, this was the actual value. What is the residual then? 95 minus 70, 65 minus 70, 40 minus 70, and 80 minus 10. So now the second decision tree actually takes these as the target, okay, and these 2 as the input variable, and feeds another decision tree. Okay, and let's say now the prediction is 21 minus 2 minus 20 and 8. Okay, now what is the overall prediction? So this is where it is tricky. So to find the overall prediction, you need to take the prediction from the first tree, need to take the prediction from the second tree. So the prediction, if combining these 2 trees, are going to be 91. Okay, and what was the actual value? The actual value was 95. So my residual is 4. What my third tree is going to do? Again, going to take this as the input variable and going to take this as the target variable. Okay, so this is how step by step your tree will be built. Here you are trying to find the residual in all steps and then fitting individual decision trees. Okay, that's the idea. Okay, and these are also given different weights based on, again, type of errors they are making, or there is another concept which is learning rate, which I will come in a short while. So final prediction is so this is the overall additive model, and final prediction is this comes from the first decision tree, second decision tree, third decision tree, and so on and so forth. Okay. So it is to be noted that as we are trying to reduce the residual step by step, the ensemble is prone to overfitting, because every time I am trying to find what is the error and fitting a tree on that. So that's the reason we directly do not use to fit the error, but we use some percentage of it. Okay, so which is denoted by this alpha 1 and alpha 2. So if the error is 4, maybe I will add a alpha 1 value of 0.3 and take the target as 1.2. Okay, and we'll try to fit my model on that. Okay, so that's what generally is done.